How are we doing? Awful. I don't like to hear that. How's the weekend? Good? Ready for the next week? I get that. Give it a few weeks, we'll be done. Yes, I understand. Our final is the first day, the 13th, 12th, whatever day it is. Whatever that Monday is, the 12th. It is the 12th, yes. The 12th at 10, same time as class, 10 o'clock, same room in here. Our test will be Monday. I'm sure, hope we'll probably have some review times too. So, anyway. What questions do you have before we finish up section 9.3 and get it in 9.4 today? All right. Well, I'm going to do a couple more examples of, pardon me, Gauss-Jordan method to solve systems of equations. I'll leave a couple more for practice for you, and then we'll get into some new stuff with matrices as well. So let's look at this next example on our handout. I've got the system of 3 equations and 3 unknowns. I know I've got a number x1, x2, x3. If you prefer to look at it as x, y, and z, that's perfectly fine. Doesn't really matter what the letters or numbers there that are given to you. To use Gauss-Jordan, first thing we create is what? What do we write down first? Yeah, do that. Yeah, exactly. We'll do that augmented matrix, right? So what's the first row going to look like here in this one?
1, 2, 3, 2.
And then again, we'll put that vertical bar down to kind of represent the equal sign. Next row will be
2, 1, 2, 0.
Good. And the last one will be
1, 1, 1.
Good. Okay. Pardon me. All right, so that's writing down our original augmented matrix, right? We're just taking the coefficients out. We need to make sure we have it in that standard form, right? We want all the variables on one side, all the constants on the other side of the equal sign. And we want to make sure that we've got the stacked idea, right? Make sure all of our x1s are over each other, the x2s or the x's, the y's, whatever you want to call it. So that we get them all the coefficients for the x or the x1 are all in the first column, for the x2 or the y are in the second column, and so on across. What's our first step? What do we want to do first? Get what where? Yeah, the upper one on the upper left. Do I need to do anything on this one to get a 1 on the upper left? No, good. The next thing to do is to do what with that 1? What do we want below the 1? Zeros, right? Okay, so first, to make that a 0, what do we need to do? Good. Yeah, we need to add -2, right? Always work off the 1 you found to get the zeros below it, right? Or above and below it, okay? So we'll do -2 times row 1 added to row 2, replace row 2. That does not change row 1 at all. And certainly the first entry in row 2 will be a 0. What's the second entry going to be? Five, good, because it's -2 times the -3, which is +6 plus a -1, right? So that'll be a 5. What will the next one be? -2. Because it's -2 times the +2 gives you -4 plus 2 gives you -2. The last entry will be -2. Now I could just rewrite the third row, but just to simplify space here, I'm going to get rid of that, make that 0 in that third row at the same time. So now to make this a 0, what do we need to do? Yeah, add -1, right? So we'll do -1 times row 1 plus row 3 and replace row 3. Again, that'll make that a 0 for sure. What do you get for the next one? So I'll do -1 times -3 gives you +3 plus 1 is 4. The next one will be -1. Good, yeah, because -1 times 2 is -2 plus 1 is -1. The last one will be 5. That one okay? All right. What's the next step now? Oh, yeah, you need to get a 1 right here, right? We'll make that a 1. No, there's in this case, I'm going to avoid the fractions if I can. In this case, there's another way to get a 1 besides one way to do it is just divide everything by 5, right? We agree with that? If I divide everything by 5, that'll make that a 1. Yeah. I can do that, but it's going to give me some fractions. There's another way I can do this without making a fraction. You see a way that I could add the third row up to the second row and make a 1? I could do -1 times row 3 plus row 2 and replace row 2. That will make it a 1, won't it? I'll do -4 plus the 5. And that way I don't get any fractions. Okay. If you don't see to do that, it's absolutely okay to divide everything by 5. You'll just have to deal with the fractions as you go. Okay. All right, so that doesn't change the third row at all. What becomes of the second row? Well, this is still a 0. I get -4 plus 5 gives me a 1. -1 times -1 is +1. -2 is a -1. -1 times 5 is -5. -2 is -7. By the way, this only worked because I could do row 3 up to row 2. I wouldn't have wanted to go this way because it would change that number there. If you don't like the little trickier way to do that, don't do it that way. You just make your fractions and that's okay. That's what calculators are for. All right. We now got that to be a 1. What's next? You get zeros above and below it, right? Gauss-Jordan says get zeros everywhere above and below those 1s. Let's get a 0 here. And we always work off the 1. So what do we want to do? Good. So we'll do 3 times row 2, add to row 1, replace row 1. That's going to give me a 1 and a 0 for sure, right? That's the whole point, isn't it? We do 3 times -1 gives me -3. Plus 2 gives me a -1 here. 3 times -7 gives me -21. Plus 1 gives me -20. And if you need to use your calculators to do the arithmetic, please do. That's okay. All right. What also, besides getting a 0 there, we want a 0 here, right? So what do we need to do to get a 0 here where that 4 is? Good. Multiply by -4. Yeah, -4 row 2 plus row 3, replace row 3. That better give me 0, 0 there, right? It's the whole point, isn't it? It's making the 4 go away. -4 times -1 is +4. -1 gives me a +3. -4 times -7 is +28. plus 5 gives me positive 33. Okay. What's the next step? Get a 1 here, right? What do we need to do to get a 1 there? Divide by 3. In that last spot, the only option you have is to divide by the coefficient. You don't have any other option besides doing that. Okay. Otherwise, you'll mess up the other zeros that you got. Okay, so we'll have 1, 0, negative 1, negative 20, 0, 1, negative 1, negative 7. What is the last row going to be? 0, 0, 1, and then 11. Good. And then finally, almost done, what's the last thing to get? 0 is above that 1 that we just found, right? So to make this one a 1 right here, what do you need to do? Is add the 1, right? Add row 3 to row 1. Again, that doesn't change row 3. We're going to get 1, 0, 0 for sure, right? We're rigging it so that it makes those zeros, doesn't it? We're doing fewer computations as we go across. What are you going to get when you add up? When I take that 11 minus the 20, we'll get negative 9. We also need this one right here that I'm circling to be 0. What operation do we need to do on that one? Add it again, right? Do row 3 plus row 2, replace row 2. 0, 1, 0. 11 plus negative 7 gives us 4. We're now done, right? We've run out of rows. What's our answer going to be? Negative 9, 4, and 11. What questions do you have on that one?
Can you explain like the trick thing that you did? Just again.
This part right here.
Yes, where you like add the.
Yeah, so I was looking at these two rows, and I know I want a 1 there. I noticed if I subtract 4, I can get a 1, and I have a 4 there, so I can just work off of that.
Okay.
Yeah. It was better than introducing fractions, I thought, so that was why I did it that way. That okay? Work on the next one for a minute, and then we'll chat about it, and we'll do one more after that. What? Okay, get a 1 on the upper left. We need to do anything. No. Next step is to do what? Get zeros below it, all right? Remember, it's always get a 1, get zeros, get a 1, get zeros, get, right? It's alternating back and forth. So in particular, we need to make that a 0. What do we need to do? Yeah, so we do negative run, row 1, plus row 2, replace row 2. I don't need to worry about the third row because there's already a 0 down there, right? Okay, what do you get for the second row? Zero, and then negative 1, 1, 4. Good. So again, we're multiplying each of the entries by a negative 1 and adding down, right? Negative 1 plus 0 is 0. 0 plus 1 is 1. 6 plus a negative 2 is 4. Is that okay? Okay. Now what's the next step? Get a 1, right? We need a 1 right here, right? There's 2 easy ways to do that in this case. What would you like to do? Yeah, I can just multiply the row by negative 1. What's the other easy way to get a 1 there? Yeah, just flip it with row 3. Either one works, right? Isn't it? Make sure you get a 1, right? We'll just flip all the signs. We'll multiply everything by -1. So we'll get 0, 1, -1, -4, 0, 1, 1, 2. What's next? You get zeros everywhere else, right? Agree? Okay. What do I need to do to get a 0 right here that I'm circling? That part. Yeah, do a -1, right? So we'll do negative row 2 plus row 1, replace row 1. What does your first row become? 1, 0. So 1, isn't it? Yeah, 1, 0, 1. So let's think about what we need to do, right? We're doing negative row 2. So negative times -1 times -4 is +4, plus a -6 is a -2. What else do we need to do? Yeah, you need to get 0 below it. Exactly, right? Right there. What do we need to do to make that a 0? Yep, -1 times row 2, add to row 3, replace row 3. Yeah. So we get 0, 0. What's the next entry? I think it's a 2, isn't it? Again, negative. Yeah, it's a 2. Yep. And then a 6. Good. Do we see where the numbers are coming from? That's kind of important, right? Getting through the process. Okay. All right. The next step now is to get a 1 where that 2 is, right? What do we need to do to get a 1 where that 2 is? Divide by the 2. Good. 1/2 row 3, replace row 3. So we'll get 0, 0, 1, 3 for that last one. And then finally, almost done, you need to get zeros where the 1 and the -1 are above that, right? So I'll need to do negative row 3, added to row 1, replace row 1. -3 plus -2 gives you -5. So you should get 1, 0, 0, -5 on that first row. The last one, we should just be able to add row 3 to row 2 and replace row 2. Bless you. And then that last entry should just be a -1. We do the 3 plus the -4. So now, writing our answers out, what do we see? Good. -5, -1, 3. Good. What questions do you have on that one? I'm going to leave the next one for practice. Let's skip to the next one. Now, you should make sure you're practicing these, right? Because you don't want time to be an issue because you're fumbling through the process, right? Make sure you practice and understand the process, okay? All right, cool. First thing here is we'll write our augmented matrix. What will the first row be? Good. And the second row will be? Good. And the last one? Good. Again, first step is to get a 1 in the upper left-hand corner, which we have. When 0 is below that 1, what should we do? To make the 3 go away, what should we do? Add negative 3. Good. So we'll do negative 3 row 1, added to row 2, replace row 2. That makes that a 0. Negative 3 times 1 is negative 3 plus negative 2 gives me a negative 5. Negative 3 times 1 is negative 3 minus 4 is negative 7. Negative 3 times negative 1 is positive 3 plus 16 gives us 19. We also need to get a 0 where the 5 is. So we'll multiply negative 5 times row 1 added to row 3 and replace row 3. Negative 5 times 1 gives you negative 5 plus the 0 gives you a negative 5. Negative 5 times 1 gives you negative 5 minus 2 gives you negative 7. Negative 5 times negative 1 gives you a 5 plus 3 gives you an 8. Are we okay with that? Those 2 steps? I know I did the arithmetic a little bit more quickly, but are we okay with how the steps are working? What do you notice to these 2 rows now here? They're exactly the same, right? Are these 2 constants the same here? No. Right? So remember, these 2 are literally the same. This says negative 5x2 minus 7x3 is supposed to equal 19 and 8 at the same time. Is that going to work? No. As a matter of fact, if we do one more step, I'm not going to bother getting a 1. But if I do negative row 2 plus row 3 and replace row 3, we get the same first 2 rows. But notice we'll get 0, 0, 0, negative 11 when we're done. That last row says what? It says 0 equals negative 11, which is not true, right? So what does that tell you for the system? No solution. Good. Remember, when you get a false statement, one number equals a different number, that tells you have no solution for the system. Let's do the next one and see what happens. Okay. Oops. Our first row will be negative 4, negative 1, 2, and then a 3. The second row will be 3, 3, negative 1, negative 1. And then we have negative 1, 2, 1, and a 2. Again, first step is to do what? You get a 1, right? Up in the upper left-hand corner. I probably don't want to divide by negative 4 to make fractions. What I'll do instead is I will swap row 1 with row 3 first. Because now to get a 1 in the upper left-hand corner, what do we need to do? I'm going to change that negative 1 into a 1. Yeah, just multiply by negative 1, right? So I get 1, negative 2, negative 1, negative 2. And the other 2 rows stay the same. Well, it took 2 steps to get there, but it's a little bit easier not to work with the fractions if I don't have to, right? It's kind of my motivation. Only use the fractions if I absolutely have to. I mean, not that they're that bad with a calculator, but generally speaking. All right, what do we want to do next now that we've got the 1? Yeah, you get 0 here and get 0 here, right? To make that 3 into a 0, what do we need to do? Good. Negative 3, row 1, added to row 2, replace row 2. You get 1, negative 2, negative 1, negative 2 is still the first row. Negative 3 times negative 2 is positive 6, plus 3 gives me a 9. Negative 3 times negative 1 is positive 3, minus 1 gives me a 2. Negative 3 times negative 2 gives me a positive 6, minus 1 gives me a positive 5. We also need to replace the negative 4. So we'll do 4 row 1 added to row 3, replace row 3. Somewhere along the line. Did I flip a negative somewhere? Oh, yep, this should be a negative 1 down here. When I flipped, I forgot my negative. Sorry about that. 4 times negative 2 is negative 8. It's easy to make a little error like that. Minus 1 gives you a negative 9. 4 times negative 1 is negative 4, plus 2 gives you negative 2. 4 times negative 2 gives you a negative 8, plus 3 gives you a negative 5. What do we notice about these two equations? They're literally the same, right? So rather than getting no solutions, what do you think is going to happen in this case? You're getting infinitely many, right? Okay. So remember what we need to do to write those. Let's go ahead and finish this off. I would do 1/9 of row 2 and replace row 2 to make a 1. I know there's not a lot I can do now except use fractions. 0, 1, 2/9, 5/9. That's making a 1. And then again, the next step is to get zeros above and below it. To get a 0 above it, we would do 2 times row 2, it's positive. 2 times row 2 plus row 1, replace row 1. Two times 2/9 is 4/9. Minus 1 will give me a negative 5/9. 2 times 5/9 is 10/9. Minus 18/9 gives me a negative 8/9. The last step to make that negative 9 a 0, we'll do 9 row 2 plus row 3, replace row 3. And we already said that it was basically the same equation. If you do 9 times row 2 added to row 3 and replace row 3, you're going to get an entire row of zeros on that last one. Okay. So remember again, the whole reason why I wanted to do this particular problem. This tells you that you have infinitely many solutions. Because that equation tells you 0 equals 0, which is true. Right? What equations are left here? What equation does the first row correspond to? Okay. Yeah, so if we use it, let's use the z's because it's probably a little bit easier. X minus 5/9 z equals negative 8/9. And what does the second row tell you?
1 minus 2 z equals 5/9.
Okay. So remember, this is ones where you write the x and the y in terms of the z to start that way. So in the first equation, we will add the 5/9 z to the other side. And in the second one, we'll subtract the 2/9 z to the other side. Doesn't really matter what letters you call them as long as you call them different letters. So then when we write our solutions, remember this means that we get to pick whatever we want for z, but once we pick the z, we know what the x and y have to be in terms of those equations. Okay? So your x coordinate will be written as 5/9 z minus 8/9. Your y coordinate will be negative 2/9 z plus 5/9, and then a z for your last one. And that would be your solution. So that's when you get your infinitely many solutions in that case. Again, any questions on the process? It's very, very repetitive, right? Okay. All right. Well, let's start a little bit of new stuff today here. Yeah, I'll get it. I can get it to go. There it is. All right, so we're going to play around with matrices a little bit. In particular, we're going to do some matrix algebra. It's probably a little bit better to call it matrix arithmetic. All right. So section 9.4 talks about what's referred to as the algebra of matrices. The first part talks about wanting to see what needs to happen in order for matrices to be equal. We've already talked about what a matrix is. Pardon. Goodness gracious. What do you think it means for our purposes for two matrices to be the same matrix, to be equal? What has to be true, do you think? We'll give another type of example here. Do you think those two matrices are the same? No. What's different about them? The 4 and the 5, right? Those two things are different, right? So in order for two matrices to be the same, what do you think needs to happen? Can I make one of them different? One of the entries different? No. I need to make all the entries the same, right? So two matrices are equal if A sub ij equals B sub ij for all I and j. Okay. Every single entry has to be equal in order for matrices to be equal. Okay? So I'm not allowed to make one entry not be the same, but all the rest of them be the same. That doesn't work. They all have to be the same. So let's see if we can answer this first example. It says solve for A, B, C, and D. Well, they're telling you that these two matrices are supposed to be equal to one another, right? If those matrices are supposed to be equal, what needs to be true? All the entries should be the same. So tell me one equation that you would get. Say you're looking at the upper left-hand entries. What equation can you get from that? So, careful. We're just looking at the upper left-hand corner. 3a has to equal a minus 6, right? Tell me another equation that would have to be true.
E minus 6 equals 2b.
Good. E minus 6 has to equal 2b. Another equation that has to be true.
2c plus 2b equals 1.
Good. And finally, a last equation that has to be true.
Negative 4b equals 6.
Good. All right. So again, all this is saying is that in order for the two matrices to be the same, upper left has to match, upper right has to match, lower left has to match, lower right has to match. So we get 4 equations here. Can we solve these? Yeah, I think we can. Whoa, that was fun. I don't know why it does that sometimes. All right. In that first one, I could subtract the a over, get 2a equals negative 6. So your a would have to be negative 3. In the second one, I could subtract b over to the other side, and I literally at that point just get b equals negative 6. I'm going to skip down to the fourth one. What does the fourth one tell you? D equals negative 4? Good. Why did I do that one? Yeah, fill in for D in the other one. Good. The other one now says 2c minus 4 equals 0. And if I go through and solve for c, you should get c equals 2. Those were fairly straightforward equations to solve, I hope. Just had to do one substitution back. That one okay? All right. So let's talk about some of the operations that we can do with matrices. Three of the simpler ones are adding and subtracting and multiplying by a number. We call that scalar multiplication. If I were to say, want to do, why do you keep doing that? Stop it. Say I wanted to add 1, 0, 3, negative 2 to 5, 1, 1, 7. What do you think how do you think you would want to do that? Yeah, good. I probably just want to match up the pieces and add them, right? Do the 1 plus 5. Do the 0 plus 1. Do the 3 plus 1. Do the negative 2 plus 7, right? Give you 6, 1, 4, 5 when I'm done. Yeah, that's exactly how you add. So if you're going to be able to add, what better be true about the sizes of both of your matrices? They better be what? The same, right? If the matrices have different sizes, you can't add them. Okay? All right. So the way we typically write this is general entries, is you would write it as a sub ij plus b sub ij. That's kind of the fancy notation for it. Yeah. All this means is that you just add your corresponding entries. And your matrices must have the same size, must have the same dimensions. Well, if you add two matrices by adding their corresponding entries, how do you think we're going to subtract? Same, exactly the same way. Again, the notation here would be a sub ij minus b sub ij. That's the notation. Not as worried about that, just showing you the notation. This just says that you subtract the corresponding entries. Oops. I should say matrices. Just say matrix. The matrices must have the same dimensions again. Okay. Scalar multiplication just means they're taking a number and multiplying it by a matrix. So as an example again, say I took the number 2 and multiply it by the matrix 1, 0, 3, negative 2. What would you think we should do with that 2? Based on other types of things that you've seen before, we have a number out in front of something. Yeah, multiply times all of them, right? Distributed kind of idea, right? And that's exactly the right idea. Take that 2 and multiply it by absolutely everything. Okay? So the notation again would just take that C times A sub ij. That was weird. A sub ij. So you just multiply each entry by that C, by that constant. Okay. And that's exactly what we do. All right. So let's look at a quick example here in the next few minutes, and then we'll do more of these next time. The first problem says to add A to D. What do you think?
Not possible.
Why not?
The matrices are different sizes.
Yeah, they're not the same size, right? So this one's not possible because what are the dimensions for A? Good. It's a 2 by 3. Remember again, we do row by column when we write it down, right? A is a 2 by 3 matrix, but D is a what? 2 by 2. They have to have the same size in order to be able to add them. All right, so if we do A plus B now, does that one work? Can I do A plus B? Yep, that one's not too bad. I take negative 2, 1, 3, 4, 0, negative 1, added to 4, 1, negative 2, 5, negative 1, 3. What do we end up with? Okay.
9, negative 1, 2, 1.
Good, exactly right. Negative 2 plus 4 is 2. 1 plus 1 is 2. 3 plus negative 2 is 1. So on down the line. The next one says do 3 times C. C is that 2, negative 1, 0, 6, negative 3, 2 matrix. What do we end up with there? 6, negative 3 on the top. Good.
0, 18.
Okay.
And negative 9, 6.
Good. Everybody okay with those? Okay. So the other ones are just kind of playing with the ideas. We'll go through more of these next time. And we'll define what matrix multiplication is, and then we'll also get started with talking about how we undo matrix multiplication. So we'll do that on Wednesday. Have a good one. I'll see you then.